Hello and welcome to Tonight at 8 from the RSGB. As you'd probably expect, radio astronomy has strong connections with amateur radio, and this evening's webinar will tell the story of one of the world's leading radio astronomy observatories, Jodrell Bank near Macclesfield in Cheshire. Our presenter is Professor Ian Morison, G0DMU, and he has been actively involved with the observatory for over 50 years, including the building of the MERLIN array in the 1980s and 90s. So it's welcome to Tonight at 8, Ian. Can you give us just a flavour of what you'll be covering this evening?
Certainly. Well, good evening, everybody. Well, obviously, from the title, I'll tell you about the history of the observatory, starting way back in 1945, but also of some of the exciting discoveries we've made and how radio astronomers do what they do and how it relates to optical astronomers. We can observe some things they can't and vice versa, but often we can actually combine our observations together, and that's great. And I also say that the arrays we have across Europe and other parts of the world have the highest resolution of any instruments in the world.
Well, it sounds fantastic. We're looking forward to that, Ian. And before your presentation, a reminder that to you at home, that if you're watching this on Monday the 6th of June, then this is live. And you can ask questions and make comments on either BATC or YouTube chat at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. But now back to Ian for the story of Jodrell Bank.
Well, hello again. Well, our story begins at the very start of the Second World War. Bernard Lovell was studying cosmic rays at Manchester University, and he was called up not to fight, but to help develop radar. And to learn a bit about it, he was sent to Staxon Wold, a chain-home radar station in the hills of North Yorkshire. And he was there the morning that war was declared. He saw quite a lot of echoes on the radar screens. He got somewhat perturbed because no one seemed to be doing anything about it. He said, "Why aren't you scrambling any fighters?" And they said to him, "Yes, there are echoes, but they are not aircraft. We do not know what causes them. We call them sporadics because they come and go a bit." Now Lovell, who'd been studying cosmic rays, knew there was a mechanism whereby a very high energy cosmic ray could give rise to a shower of electrons that could reflect radio waves. So he wondered if radar could be a way of studying cosmic rays. So when the war ended, he got hold of some army radar equipment and set it up in the field about 20 miles south of Manchester, where the botany department were doing some crop trials. There was far too interference problems at the university itself in Manchester. And there you see, I think, the receiving antenna system adjacent to two wooden huts, where they put all their equipment, in fact. Notice the little sprig on the left-hand side. In fact, over time, that actually grew and grew and grew, and now totally envelops that left-hand hut. Well, they got their first echoes on the 14th of December 1945, and they got a lot of them. And it was actually some serendipity there, because that was the night of the Geminid meteor shower. And they soon realized that they were not detecting echoes from cosmic ray air showers, but in fact from the trains of ionized gas left behind. A little dust particle comes into the atmosphere and burns up as a meteor. So it wasn't what they were hoping to discover or investigate, but it was interesting. So they carried on, and in fact the first book that Lovell wrote was all about meteors. Well, things went well, and the university decided that things should carry on, and they built what was then called the Jodrell Bank Experimental Station, which is in the field, in fact next to the one where Lovell had started his observations, which was down just off to the lower right of the picture there. And there you can actually see the station as it was. We'll zoom in a bit. It's actually lying about 20 miles, as I said, south of Manchester, between Alderley Edge and Holmes Chapel on the M6. We've zoomed in a bit, and you can see, in fact, three antennas, I think, there. There's one here called the searchlight antenna, which you'll see again in more detail. There's a rather small little antenna over here you can barely see. But here, in fact, you're seeing but not seeing what was then the world's largest radio telescope. And the reason you can't see it is because the surface of the dish was made with a wire mesh. It just doesn't show up. But perhaps you can just see the little white spot up the top here. And that's the feed, where the radio waves reflected from the surface were actually concentrated. Now you might say to me that a telescope just looking straight up, fixed, is no use at all. But in fact, of course, as the Earth rotates, a strip of sky comes overhead in each 24-hour period. And by tilting the mast, as we shall see, you can actually look at another strip and another and another, and gradually build up a radio map of the part of the sky that comes, broadly speaking, overhead at Jodrell Bank. This is a picture of that searchlight antenna system. They used a searchlight base because they could move it all around the sky. We say that's fully steerable. And here is Lovell. I think on the day he was appointed the first professor of radio astronomy in the world. Some of the people here I know. My boss for a while here was Professor John Davies. Over here, interesting guy, Dr. Tom Kaiser. Now, he was a communist sympathizer, that was known, and some of the staff were having Russian lessons in the room above the bar at the Red Lion pub just down the road. It was thought he might have been a Russian spy. And this rather clean-looking chap over here, in fact it's called Ian Brown, I found out recently, although he was doing a PhD, was also an MI5 agent, keeping an eye on Tom Kaiser. Now he obviously wasn't a Russian spy, he actually went to become the Professor of Electronic Engineering at Sheffield University. So we're zooming in again. You can see that telescope. Over here is the powerhouse. Obviously we weren't on the grid, we had our own little power station there. And these were the various laboratories. This is called Park Royal because in fact I think they first brought a Park Royal trailer there to make their first observations. So I said there's that telescope, and by tilting the mast you could gradually, day by day, look at a different strip of sky overhead and gradually build up a crude radio map of the sky. I say crude, it's not terribly detailed because they're working at quite a long wavelength. But that made some very nice discoveries. There's a nice look at it over here, but a bit later in time you can actually see the two wooden huts over here, and that little sapling is now quite a big bush already. Here is the dish, and that's the mast, which actually is now at an angle so they could put a new feed at the focus. That's the powerhouse. This is a little telescope, 25 feet across, and it is a fully steerable telescope. It's mounted on the two towers here and here, and therefore could be rotated up and down, and you can see the central pivot, which is there, around which the telescope could be rotated. So it could actually look at any point in the sky and in principle follow objects as they go across the sky, and that allows you to integrate the signal and hence pick up weaker signals. So this is one of the first discoveries they made with that telescope. In 1572, Tycho Brahe and obviously others observed the supernova in Cassiopeia. And he, with other observations, showed it lay beyond our solar system. And that was a problem because in those days it was taught that the stars were perfect. Nothing could change there. This obviously was something new. Now, you can't observe it now optically, but we can see it with our radio telescopes. Perhaps more significant, they were able to make a very rough radio map of the Andromeda galaxy. It's 2.5 million light years away. It's the largest galaxy in our local group of galaxies. And this showed for the first time that we could receive and detect radio waves from objects well beyond our own Milky Way galaxy. And Bernard Lovell realized if only he could have a telescope about that size, if not bigger, that could actually be fully steerable, could actually look at any point in the sky and track objects across the sky, it would be a fantastic instrument. And he got an engineer called Charles Husband to design what was to become known as the Mark I radio telescope. And as you can see there, it was going to have a wire mesh surface. But for various reasons, and I suspect one of them was military, it was decided to give it a steel surface, which made it a lot heavier. The backing structure had to be considerably more expensive. Well, they're laying the outer railway track around which the telescope rotates, and that's the central pivot about which it rotates. Here you see one of the two towers being constructed. At the top, you can see that round object. In fact, there's a cone that comes up to that flat plate from a very big bearing, and just behind the flat plate, there in fact is a great gear ring, and two gears mesh onto that to rotate that around one way and the other. And that's how they could adjust the height of the dish in elevation. They were in fact second-hand. They came from Rosyth Dockyard near Edinburgh, where they were dismantling some World War I battleships, and they were in fact 15.5-inch gun turret mountings. You can perhaps imagine that moving around a heavy gun in azimuth is not that much difference to moving a big dish in elevation. There it is, construction underway. Here we have two of the driven bogies, the two on each side, that drive the telescope around, we say, in azimuth, round and round. And there, it's getting there, a nice picture in colour. Looking down from above, you can actually see them building the focus tower, at the top of which they put the feed aerials, and in later times a focus box in which we put our receivers. Now, some of you may have heard of the Tacoma Narrows Bridge disaster. This suspension bridge started oscillating and finally broke up under a steady wind condition. It wasn't gusty. Well, now, Lovell gave a talk about the Mark I telescope at the National Physical Laboratory at Teddington in London. And afterwards, one of the scientists there came up and said, "Dr. Lovell, have you put a model of your telescope in a wind tunnel?" And Lovell said no. He said, "Well, I just think it might be a good idea to do so." So they built a 10-foot diameter model. It went into a wind tunnel. It lasted about 5 minutes. It started oscillating and broke up. Well, to stop that oscillation happening, they had to add an additional part to the structure. It's called the wind stabilizing girder, and you can actually see it here behind Lovell on the right and Hubble on the left. There it is. We actually called it the bicycle wheel. And that applies friction, and the telescope would not therefore oscillate. It's a very lovely view of it, actually, looking across from the original 218-foot transit telescope. You can see that smaller telescope I mentioned earlier just here. Well, I think you can see that the Mark I telescope was really just that one scaled up by quite a bit. So it's a very nice view. Now, going ahead in time, you can perhaps just see that little white oval here. That's part of the 50-foot diameter telescope. And we used that in later times to track the Apollo astronauts to the moon. And this is in fact the plot of the landing of Apollo 11. It was coming down smoothly under computer control, and that's what you're seeing, this lovely smooth curve here. But Armstrong, who was piloting the craft, realized they were about to land in a crater. He took manual control, he lifted up the spacecraft a little bit and flew rather jerkily over the surface until he actually reached the surface at this time here. I think that was pretty good proof that the Americans actually went to the moon. We don't worry about it now, but they did for a while. And there was a film in 1982, I think it was, or 92, sorry, where in fact the Canadian broadcasting company put out a film rebutting one by Fox Television, saying they didn't go, saying of course they did. And in that film, I was actually describing this plot and what we observed at Jodrell Bank, intercut with Buzz Aldrin saying exactly what had happened, and it fitted like a glove. Well, here is the control room, as it was, of the Mark I telescope. We had a fundamental problem. The engineers who were actually commissioning the hybrid analog mechanical computer you see over here that was used to drive the telescope had walked off site. They were not being paid. Husband was about to sue Lovell for non-payment of fees. And I did hear, not that long ago, the university were considering sacking him. But we were saved. We were saved by the launch of Sputnik 1. The military were very keen to know if you could detect rockets by radar to give us an early warning radar system. And so phone calls must have gone out from the Ministry of Defense. The engineers came back. They commissioned the telescope in double quick time. A powerful radar system was attached to it. And it wasn't that long before, on the 12th of October, we were able to detect the third stage rocket that was actually following Sputnik as it crossed over the Lake District. And that's Lovell showing the press the radar echo. So instead of being a white elephant, it was shown that we had something in the UK that no one else in the world had. And for quite some time, it played a major role in what we might call space tracking, helping both the Russians and the Americans. We followed Luna 2 until it crashed into the surface. The Russians would tell us the right frequencies to observe on and when and where. And that was so we could actually prove to the Americans that the Russians were doing what they said they were doing. We also helped the Americans. They built an enclave, which is over here with their equipment and their antennas. And the idea was that the Lovell telescope would command their first rockets in the separation of the stages and also bring back the telemetry from them. And it was all done in top secrecy. However, a lot of the equipment came in a very large van and trailer, and that's been towed here. And it was actually spotted by a journalist from the Manchester Guardian, as it was in those days. And on the side it said, US Air Force, Project Able, Jodrell Bank. So the secret was out. Well, when the first rocket went up, it actually exploded not far from the launch pad. To be honest, that slightly pleased Lovell, because he was hoping to go and play cricket. He was the captain of the Chelford cricket team, a little bit to the north. But the second of their craft didn't quite get to the moon, which they had hoped it would, but it carried a magnetometer built by someone called Van Allen, and it discovered what are called the Van Allen belts. And that was really the first bit of scientific research that came out of the space race, and Jodrell Bank was involved. So there we have the Van Allen belt, a radiation belt which is trapped by the magnetic field, and that actually prevents a lot of nasty things impinging on the Earth's surface. Well, I arrived at Jodrell Bank in autumn 1965 and was given a pretty horrendous PhD project, which was happily successful in the end, to study the surface of the moon by radar. So when the following February, the Russians soft-landed Luna 9 on the surface of the moon, I was able to join in a bit. Now, the signals that came back were recognized so that if we had a device called a Muirfax machine, which was used to send pictures across the world really by telephone before the days of the internet, then we might be able to decode what we thought were pictures of the surface. All of the top knobs were up in the control room. You've seen that, watching what was going on. But I was actually down in the sub-basement where the Muirfax machine was. And I was there with the Daily Express. They'd brought it to Jodrell. Their operator was there. And in fact, when the first signal came, once we'd hooked it up, a little a stylus moved back and across the film, exposing it electrically. And I helped process that plate. And he and I were the first people in the Western world to see what the surface of the moon looked like in close-up. So when you're 21, that's quite exciting. In fact, I actually realized it wasn't really looking very good. When we tilted the image, it looked a bit better. It flattened out a bit. Well, I went home quite late that night, and in the morning my wife brought me the paper and a cup of tea, and on the front of the Daily Express was in fact this picture, the one you see here. And in fact, I realized there was something wrong with it. So I got up very quickly, I rushed into Jodrell Bank and said, Dr. Lovell, he may have been Sir Bernard by then, there's something wrong with our picture. We've got to stretch it out. by about 40%, pull it out from each side. They've used what I call an anamorphic lens, which I did actually know about. He said, I know, Morison, the Russians have just told us. And in fact, I was right, and perhaps that's why I'm still there. Well, at times recently, we have done a little bit of what we call space tracking. Only when people like NASA ask us kindly to do it. We've searched for two of their missing spacecraft at Mars. The one on the left we think actually blew up when they fired the retro rockets to slow it down to orbit Mars. And the second one we think sadly crash landed. So that was unsuccessful. I was actually a very minor project scientist in a way for the Beagle 2 mission, you might remember. Beagle 2 was built at the Open University under Professor Pillinger, and it was due to land on Mars, on the surface, on Christmas Day 2003. It was carried there by a spacecraft called Mars Express, and I was actually in London being able to watch how Beagle was ejected, in a way, from Mars Express and sent on its way to Mars. Now, they only have very low power transmitters, as you can expect, and that's in fact the antenna I think you can just see here. So what they normally do, and all of these landers do, they relay their signals up to an orbiting spacecraft, or they send their signals up to an orbiting spacecraft, which then relays them back to Earth. Now, Mars Express wasn't going to be in the correct orbit for quite a few days, and obviously they were very keen to know if Beagle had landed safely. So I was charged with setting up a receiver system to use with our Lovell telescope, which is what we now call it, to detect those signals directly from the surface. And I tell you, our telescope, because actually of its shape and the way it works, is the best telescope in the world for observing the low frequency signals that Beagle would have sent. So we were there on Christmas morning 2003. I think we got there at about 5 o'clock. You can actually see Mars is there. It was a lovely clear morning. Sadly, we picked up nothing. We had a fantastic receiver system. It used, in fact, some high temperature superconducting filters to help get rid of a lot of earthbound interference. This is the image screen that we were looking at. It's called a waterfall display, and I know there are in fact some radio receivers now that give you waterfall displays, so perhaps many of you know what I'm talking about. Normally when I give this talk, people don't. This is frequency across here, and this is time. Now, I think you can see there's a vertical line there pretty well, and there's one there. So those are signals whose pitch, whose frequency is not changing with time. They are basically ground-based, probably interference from Jodrell Bank itself. But I think down here on the lower left, can you see that little curved line? Well, that's a signal that's changing its frequency, the Doppler shift. That's a satellite orbiting the Earth. But over here, you might just make out a curved line, very slightly curved line up here. Our eyes are very good at this. That is in fact a satellite orbiting the Sun. This was a very, very sensitive system. And Beagle 2 should have been marching up the center. We'd actually had a trial version which we were able to test at Jodrell Bank, but there was nothing there. We actually looked for it for about a month on and off, to no avail. And no one knew what had happened until some years later, when an orbiting spacecraft spotted the landing site. It found the parachute, the cover, and also Beagle 2 itself, and it zoomed in, and this is what they saw. It should have had 1, 2, 3, 4 solar panels, but can you see only 2 of them have opened up. So it landed safely in one piece, but sadly didn't quite work. The saddest thing of all about this was it was found about 2 months after Colin Pillinger, its father really, had died. That was a real pity. But I was very pleased, very proud to be part of the whole exercise. Now some astronomy. The first significant experiments I think that were done with the Mark I telescope was when a smaller 35-foot telescope, which was portable, was taken around the country. Firstly across Cheshire into Wales, and then over into the northeast of England. The signals it picked up were sent back to Jodrell Bank by microwave radio link, which you see there. By combining them with the Mark I telescope, as you gradually move them further apart, you could actually finally work out the angular size of the objects that we were observing, the radio sources as we call them. Now, you may well know that the angular size of the moon and the sun are 30 arc minutes, half a degree. It's the same, which is why we actually see these lovely eclipses of the sun. If you have an object photographed by a telescope in those days, the smallest size you'd actually be able to see on a photographic plate was probably about 2 arc seconds, and that's caused by atmospheric turbulence. Well, that means that anything that's less than 1 arc second in size would look like a star. Well, with that system, out of about the 300 then known radio sources, we showed that 7 of them had angular sizes less than 1 arc second, so looking like a star. They were thought, in fact, they might be rather special stars in our own Milky Way galaxy. But it was shown that in fact they were not. This is a photograph taken by the Hubble telescope. That was the world's largest telescope then. These are stars there, and here, but that looks like a star, and if there was nothing else, you'd say it was a star. But can you see the jet? And by the time this image was taken, we'd managed to make a little radio map, using the moon actually, showing a bright pip in the center and a jet. It exactly corresponded. A wonderful astronomer, Martin Schmidt in America, took what's called the spectra, the signature of that object. And after quite a while, he discovered that he was seeing the hydrogen lines, H, beta, gamma, and delta, you just see here, here, and here, which were shifted a vast amount from where they ought to be. It's called the redshift. And from that, he showed that this object was not 2.5 million light years away, like the Andromeda galaxy I showed you, but 2,500 million light years away, then the most distant object known in the universe. A second object that we discovered, 3C, or at least discovered where it was 3C48, and that was actually about 7,000 million light years away, which actually is looking about halfway towards the edge of the visible universe. So these were then the most distant objects known. But they were very bright. 3C273, this one, I can actually observe an image with a 12-inch telescope in my back garden. Seeing how far away they are, can you see how much energy they must be emitting? It was worked out that nuclear fusion, which powers our sun, couldn't actually give enough energy for them to be so bright. So it was surmised that the only way these could work was if there was in fact a supermassive black hole, material would be accreting onto it. As it spins round and round, it gets very hot, actually at X-rays, but also before the material goes in, some of it gets ejected as beams of light and radio waves along the rotation axis of the black hole. So I think our observations and those of our colleagues, optical colleagues, basically gave the idea that these large galaxies must be surrounding a supermassive black hole, as has proved to be the case. Well, by 1969, the steelwork at the top of the towers was showing a fair bit of metal corrosion. And it was decided that they had to take a lot of the weight away from the bowl. From the two areas here and here. So they added 2 semicircular wheel girders. You can see them there. That took quite a bit of the weight away from the towers, but it had to be balanced about its center of gravity, about here, this rotation axis. So they had to build a new surface which was within the old. It was actually smoother, and it was actually less curved, which actually made it more efficient. Although at that point, the focus box, the feed, came outside the surface of the dish, so was more open to interference. Just notice this little building here. It's called the Marconi hut. Now we all know Marconi made radios. They also made radars, and that was in fact used so that the Mark I telescope could actually be the UK's early warning radar, from about 1960 to 1963. So we did play a role, happily not required, in the defence of the realm. So there we have a parabolic surface reflects the radio waves to what is called the focus. And that is just below the focus box. You might just see a little black thing there. In there we have our receivers. They're now made with some very, very clever transistors. They're not all that much better than the receivers you might have in a satellite dish, which are now, of course, very good. They cost about 20 quid. But in fact, ours in total cost about 20,000. Because we locate them within what's called a cryostat, you see it here, which is cooled by the expansion of pressurized helium. And we get the temperatures in here down to something like 12 to 15 degrees above absolute zero. And that, in fact, reduces the thermal motion of the electrons. And so those receivers are very, very sensitive. A slightly sad thing is that the receivers we've made over the last 10 years or so are about as good as the laws of physics allow you to make. In the past, we've always been able to build better, more sensitive systems by improving our receivers. Now that's no longer possible. Well, having built the Mark 1A telescope as it was called, which is the horrible name, and on its 30th birthday we renamed it the Lovell telescope, and that's how I will refer to it for the rest of the talk. And Lovell asked his staff what might they do with it. And Dennis Wall said, well, let's make a survey of the sky around the Plough. That's in the northern hemisphere, you may know where it is. And in that survey, they discovered a rather interesting object. It looked like, on photographic plates, like a little peanut. You can perhaps see it down on the right here. When that was imaged with the Hale telescope in America, and another very good one, it was seen that we weren't actually looking at two little objects. There were three. Now, you can see that the top one and the bottom one show what are called diffraction spikes. And they tell us that those objects were sort of point sources. They were, in fact, quasars. I talked about looking like a star. We gave these objects the name quasar. But the one here, perhaps seen better there, does not show the diffraction spikes. It's a galaxy, which is about halfway between ourselves and the distant quasars. But when they took the spectra of those two quasars, they were found to be essentially identical. We were looking at identical twins, except we do not believe identical twins exist in space. So what is going on? Well, it's all down, as you might expect, to Albert Einstein. He says that if you put a massive object into space, it distorts the space-time around it and deflects light and radio waves. And what's happening is, here we're looking directly at the quasar. But the light that would have gone down below the galaxy here, so down where we couldn't see it, is actually deflected round, so we are seeing a second image. It's called the double quasar, and this was the first observation of what's called gravitational lensing. In fact, there's a time difference between the time we see the image here and the one here. It's 472 days. So obviously this has taken a longer path. It's gone down and up as opposed straight to us. And from that, we actually got a value of what's called Hubble's constant, which is the expansion rate of the universe. We've got about 68 plus or minus a large amount, perhaps 12 I think it was, not very accurate. But 68 is about the current best value, although I should say there is some controversy about that. Well, on the 2nd of January, we had some very high winds in the northwest, not quite as bad as the ones you had in the south at some similar time. And the telescope nearly blew over. So we added some cross struts, can you see there and over here, just to make it somewhat more rigid. In the high wind, we actually align the towers along the wind axis, and we rotate the telescope around as the wind direction moves. So some more astronomy. We'll talk about this a little bit later, but if you could actually go a very, very long way out into space and look back at our Milky Way galaxy, it would look something like this. And I'll show you some more pictures later on. If we look at it from the side, we know it has a central bulge and a flat disk, a lot of dust along the center of it. And our sun is well to one side. We're about 27,000 light years or so away from the center. And this actually is a painting. It's an all-sky image built or produced by the London Observatory, showing the stars of the Milky Way, also the large and the small Magellanic Clouds you can see over here. Here's the Orion constellation, the 3 stars of Orion, pointing down to Sirius, you might know. This is a dark dust region called the Cygnus Rift. So that's what you can see visually. This is a slightly garish image of a radio map of the sky. Some things we see the same. Can you see that's the large Magellanic Cloud? If I go backwards, can you see? It's the same place. And there's a small Magellanic Cloud as well. So there's some things here we can see that optical astronomers don't see. But look over here. This is actually Orion. And up here in Taurus, there's a little blue blob, which means it's slightly brighter than the surrounding. Well, if you look at that location, you actually see what's called the Crab Nebula. It's a supernova remnant from a supernova that exploded in the year 1284. And we know that these supernovae give rise to something called a neutron star. In fact, you can actually see it there. It's that little star there, just below that brighter one. This is the remnant of the supernova core. It's collapsed down. It's about the size of Manchester, about 20 kilometers across. And it might look a little bit like this. Very small. It has an incredibly powerful magnetic field that's being compressed. And as it spins around, because as the core collapsed down to its current size, it was moving around slowly. It would go faster and faster and faster, probably initially spinning perhaps 50 times a second. And it so happens that the effect of this and the magnetic field is to send out beams of usually radio waves, sometimes light, along the rotation axis in the 2 directions, as you see there. Now, if we look at it from here, and I'm hoping I can make this go around, this is what will happen. If one of those beams happens to cross our location in space, every time it does so, we get a pulse of radiation. And they're very, 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 very regular. These are very good clocks, albeit slow ones. And in fact, the name pulsar has been given to these objects. You've probably heard of that. Well, the very first pulsar was detected by Jocelyn Bell at Cambridge. She saw on a chart little pulses, just over 1 second apart, little blips on their chart recorder. Now, I can't show you a chart recorder, but I've actually observed this same pulsar myself, recorded the data. And if you play that data onto a loudspeaker cone, each little blip that you might have on a chart recorder causes the cone to give a little jolt. And that gives out little clicks. I'm hoping this is going to work. We haven't tried it before the start. Let's see. I hope you can hear the little clicks. 1.25 seconds apart. There's a lovely one in the southern hemisphere in the constellation Vela. This is spinning around 11 times a second now. And that one in the Crab is spinning about 30 times. If you actually look at these little pictures, this is that central part. And here you do not see the neutron star. The beam is pointing away from us. As you come up here, at this point it just becomes visible. And here it becomes even brighter than the adjacent star. It fades away again and comes back. So this is our views of the rotating beam. Now, stars and hence neutron stars and supernovae lie along the plane of the Milky Way. That's where all the stars are. We don't see the Milky Way terribly well from the north of England. You see it a lot better from the southern hemisphere. And so we built a multi-beam radio receiver system, you see it there on the right, which was mounted on the Parkes telescope in Australia, in New South Wales. There's a lovely film DVD called The Dish. You may remember that Armstrong spoke to Nixon from the surface of the moon, and those signals were relayed by that telescope. And the rather lovely film The Dish was about that. It's a bit of a comedy too, and I'm sure you can get it for about £5 from Amazon. It is well worth having a look at. Well, with this new system, many new pulsars were discovered. The ones we knew in the northern hemisphere, you see there in black, but all these ones in the southern hemisphere that were discovered with that system are there in red. Using a supercomputer at Jodrell Bank, one of our students, who's now a professor as you might imagine, discovered that one of these neutron stars wasn't in fact one, it was a pair of co-rotating neutron stars. We call it the double pulsar. I think the one on the right's not spinning as fast as it could do, but you get the idea. And we come back to Einstein again. He says that if you have two co-rotating massive objects, they will give off what are called gravitational waves. I'll move on so I don't hypnotize you. And these, in principle, mean that energy, it does mean that energy is being lost from the system. And so gradually they spiral in towards each other. And at the present time, the rate at which they are moving together is about 7 centimeters per day. And we can actually measure that very accurately. We've done so. It's wonderful proof of Einstein's theory. And we actually were awarded the Descartes Prize. I've got to move on there for it. And there's Albert Einstein looking as he should look. So that was rather nice. It's a lovely proof. I think this is the best test bed of general relativity that we currently have. And in fact, our Lovell telescope spends a lot of time observing this particular neutron star system. Now, if they're gradually getting closer together, eventually they're going to coalesce into one. This is a little animation. The green grid there is space-time, and you can perhaps just begin to see some ripples. And these are the gravitational waves rippling out from it. As the two get closer together, they spin faster and faster. The ripples get more rapid, and you can see here, eventually the two will coalesce. And when they do so, as we'll see in just a moment, you get what I can only call a gravitational wave tsunami. And there it goes. There it is. And what's left behind will probably become a black hole. Sorry, I have to move on that way. It's also predicted that these objects will, it is said 2 seconds later, give off a gamma ray burst. And that's because I think that comes from near the surface of the star, and the energy has got to, a shock wave has got to move out from the core, where in fact we have the collapse. Anyway, they say it's about 2 seconds later. Now, you may have heard of the Laser Interferometer Gravitational Wave Observatory called LIGO. Initially, there were 2 of these, one at Hanford in Washington and one at Livingston in Louisiana. And at each site, there are 2 right-angled arms about 4 kilometers long. And there's a incredibly, that's the one at Hanford, and that's in fact a new one that came into operation called Virgo near Pisa in Italy. A light beam, a laser beam, is split into 2 and sent up and down both of the 2 arms and then recombined. And they adjust the phase so that the 2 cancel out. If a gravitational wave comes along, momentarily one arm might get slightly longer and the other one slightly shorter because space is distorted. And that actually means that the 2 waveforms which were out of phase come into phase and you can detect them. Well, on the 14th of August 2017, the direct detection of the gravitational wave produced as 2 neutron stars coalesced into a black hole were observed both at Hanford, Livingston and also Virgo, although you can see that the signal was a lot weaker. Because there were 3 detections, oh, there's the chirp, I should have said. Can you see how as they get closer and closer together, the rate at which they rotate around each other goes up, conservation of angular momentum, until you get this final little dying burst. And in fact, there was a gamma ray burst 2 seconds later, because there at the bottom is the LIGO plot. You can see where it actually happened. And the Fermi Gamma Ray Observatory picked up a signal just 2 seconds later. That's a wonderful confirmation, in fact, that gravitational waves travel through space at the speed of light, the same speed as electromagnetic waves. Because there were 3 detections, they could actually work out roughly which direction it came from. And there you see that little green oval is where it's most likely to be. And every radio telescope in the world that could see that part of the sky would look. Sadly, we could not detect it using our Lovell or MERLIN arrays at Jodrell Bank, but it was found, and we know exactly where it was. It was, I think, 130 million light years distant. So that's really a rather wonderful bit of physics, I think. And another interesting thing that came out of this, we used to think that heavier elements like gold, polonium, uranium were produced in supernova explosions. But people were worried that there was not enough energy released. But it turns out when 2 neutron stars coalesce into a black hole, a vast amount of energy is released, and that's probably produced the great majority of all of the heavy elements. Can you see 40 there's a gold Ag, silver, and most of that being produced in a neutron star. So you get the idea. So that's something that's come out of this, which is quite new. Now, black holes, interesting. If you have a black hole in a binary system, matter can be pulled from a companion star and cause X-ray flares, which make its presence known. And that's the sort of idea. A star has given rise to a little black hole on the right there. A very massive star can leave a black hole behind. The adjacent star has come to the end of its life. It's got much larger, and so the surface material can actually be pulled onto the black hole. It spins around and round and round. Here, because of the friction, the temperature goes up to about 1 to 2 million degrees, and you get lots of X-rays. And in 1975, the Ariel 5 spacecraft built by Leicester University discovered the largest X-ray flare that had ever been observed, and since, in fact. It came from a point within the constellation of Rhinoceros. And this is the flare. And the largest one known before came to about here, and look what happened. Notice it went up on the 8th of August, 75. Now, you might say, what do academics at universities do in August? And the obvious answer is that they go on holiday. And every of the academics, that's the academic staff, the lecturers, etc., at Jodrell Bank, were on holiday, except me. And that's not because I'm a stickler for work. It's because Macclesfield in those days was still what's called a silt town, and we had our Barnamy holidays in June. And that was a much better time to have our holidays, as you can perhaps imagine. So I was back at Jodrell. And on the afternoon of the 8th, I was rung up by Ken Pounds, Professor Ken Pounds, saying, look, we've got this object somewhere in Rhinoceros. We knew roughly where it was. Can you look for it and find out where it is? So I basically immediately tried with the Mark II telescope. That's the one on the left. But that was not capable at the time to detect it. But a few days later, we linked it up with a second telescope, the same size, called the Mark III. I was using that with one of my students to study these quasar we talked about, these quasars. And we basically did a survey of that part of the sky. It was done on a paper chart. I think the chart in our lab was about 20 feet long. It had lots of lines from different angles and declination. Where they thought it was in the middle, we actually found it about 2 inches from one end. So we actually got the precise location of the system. And that meant it could be observed. There was, in fact, a star there about which the black hole was rotating. They're actually co-rotating. We knew the precise position pretty accurately. And that's the sort of idea. I've had to make the black hole visible, but the two co-rotate around their common center of gravity. If you know the mass of the star, which we did because we knew what type of star it was from its spectra, we were actually able to then calculate the mass of the black hole. It turned out to be 9.7 solar masses. That's far higher than you can have with a neutron star. So it was in fact, for many, many years, until about last year, it was the nearest black hole known to the Earth. I was quite proud of that because I'd sort of helped discover it in a way. But now, in fact, one's been found a bit nearer. Just a little bit of lightweight stuff. You've probably heard of SETI, searching for ET, the search for extraterrestrial intelligence. I was the project scientist in the UK around the year 2000, where the SETI Institute were able to link up the world's largest optical radio telescope at Arecibo in Puerto Rico with our Lovell telescope. Basically, every day, about 6 weeks per year for 5 years, we had observed sun-like stars, stars like our own, because those are the ones that are most likely to have planets with life on them. We observed about 800 odd stars. The Arecibo telescope would pick up any signal that looked interesting. Immediately, using a fiber optic link, our Lovell telescope would look at the same object. The frequency had to be different because the Earth is rotating, and we could say whether it was a real signal or just interference. So the equipment came in 1998. We observed 820 sun-like stars out to about 200 light years. It was the most sensitive system ever built to do searching for SETI. No signals were detected. ET did not phone home. But did our system work? If we got no results, how do we know the system was working? Well, every day before we started our observations, we both observed the signal from Pioneer 10, which was then 10 billion kilometers away. So we knew the system was working. Should we be surprised that ET did not phone home? Well, not really. First of all, we were looking out to 200 odd light years. Our Milky Way galaxy is 100,000 light years across. We were looking in our backyard. Unless intelligent life was incredibly common, we honestly couldn't have had much hope. Now, I do give talks about the search for life beyond the Earth, and I have to say that my current view, and I noticed that Professor Brian Cox said exactly the same thing on a program the other day. He must have watched my talk some years ago. Basically, I do believe that very simple life forms, single cell objects, organisms, will be very common on planets in our galaxy. But I think we are probably, almost certainly at this time, the only intelligent life in our Milky Way galaxy. And there are many reasons for that I won't go into now, but I do think we really are something rather special. Now, just to say that you don't necessarily need a very large telescope. And some years ago, quite a few years ago now, a colleague of mine and I built up a system using a 7-meter radio telescope. Here you see it with the Lovell telescope beyond. And I did the instrumentation for this and the control systems for it. And it was used to observe the hydrogen line. Now let me say what it is. Out there's a vast amount of hydrogen, as you might expect. But it so happens that there are two states near the ground state, basically, essentially the ground state, has two types. Either the proton and the electron are spinning in the same direction, or they're spinning in anti-parallel. If you get, very rarely, a transition from one to the other, you get a photon emitted, a radio photon, with a 21 centimeter wavelength, a frequency of 1420 megahertz. Now, that's very, very useful. And that's what this particular telescope and system was aimed to look at. Supposing you have a cloud of hydrogen gas which is at rest with us. In fact, that would be the gas within our own spiral arm of our Milky Way, as we shall find out. Because in that cloud of gas, the hydrogen atoms are all moving around, then some will be coming towards us, some going away. So you don't get a single narrow spectral line. You get sort of a Gaussian spread like that, depending on the temperature of the cloud. If that cloud were moving towards us, as in B, the whole of that shape shifted upwards. If it's going away, as in C, it's going away from us. If you were looking through several clouds of hydrogen, one going towards us, one at rest and one away, you get a signal a bit like D, and it's not too hard to split it up into the three components. So here we have obviously three clouds of hydrogen, one fixed relative to us, one going away, and one coming towards us. And with our 7-meter telescope, we could measure the spectra as we looked around the Milky Way. And the important one is over here. We don't see one blob, we see 1, 2, 3, 4 blobs. These relate to 4 spiral arms. So our galaxy has got structure. Here you only see one, and that's because we're looking directly away from the center of the galaxy, and all the hydrogen beyond is moving at right angles to the line of sight, and so there's no Doppler shift. So everything's concentrated at the rest frequency. So this, I think, proved that we have some spiral structure. You don't need a big telescope to do that. And in fact, we did a project with schools all over the country with Rotary International. And together, we measured all of the angles around the Milky Way we could see and built up a map of the spiral structure. This is just one part of it. It's actually showing the spiral arm in which we live, the one here, but also out here is called the outer arm. So we had a pretty good idea of the structure of our Milky Way as measured by hydrogen. Not long afterwards, this picture came up from astronomers who'd been using a spacecraft looking in the infrared, and that is what they produced as an image of our Milky Way. It has a bar. That's right. I did not like it, as I suspect other people didn't. Not many people have actually measured the spiral structure in hydrogen. It looked too tightly bound. Anyway, I let them know, as I expect others did, and it didn't take very long before that picture came out, which agreed perfectly to us. We're actually about here. This is that spiral arm here, and this is the outer arm. So we were looking, that bit I showed you was about here. And there we are, that's the Perseus arm. We actually live in what's called the Orion Spur, and there's the sun. So the Perseus arm, the outer arm. So that, I think, is what we think the structure of our Milky Way is. And maybe I had a very tiny role in getting that right. I don't know. Something else we could do with that little telescope. We could weigh a galaxy to find evidence for dark matter. So this is using that same 7-meter telescope. Now, I have taken a rather lovely image, well, it's one of my best images, of a galaxy called M33 in Triangulum, using a rather lovely telescope, which actually is in Spain. And this is the image I've got. We know from Cepheid variables how far away it is, so we know the size of it. That's important. And what, in fact, we measured with our little 7-meter telescope was the spectrum. Now, 0 is where our local rest frequency is, where our own arm of the Milky Way would appear. This is obviously shifted down to about minus 175 kilometers per second. It tells us, in fact, that that particular galaxy is coming towards the Milky Way at 175 kilometers per second. And in fact, M33 and M31, the Andromeda galaxy I showed you earlier, are going to coalesce with our own Milky Way galaxy around 4,500 million years in the future, so don't worry about it. So that's the first thing. However, it's not just a single spike, it has a width. And that width is about 200 kilometers per second. And that tells us that the galaxy is rotating. The outer parts on one side are coming towards us at about 160 kilometers per second, the other away from us at 160 kilometers per second. It's rotating. Now, from the actual rotation and the size, that's the formula we can use, we can calculate the mass. Don't worry about the formula, but it's not too difficult. And when you put the numbers in, as I've done there, you get 45 billion solar masses, which is quite a lot. However, if the makeup of M33 is the same as our own Milky Way, which we suspect it would be, something called the mass-to-light ratio will give us a value based upon the mass of the visible matter in our own galaxy. And that comes out to 8 billion solar masses. So there's 5 times more mass that must be invisible to us. So that, in fact, is evidence for this thing that we call dark matter. And you can do that, you see, with a very small telescope with quite a simple receiver. I think it's rather fun. Just out of interest, on the Lovell telescope's 50th anniversary, I was asked to set up, as I'm a radio amateur, a EME moon bounce experiment, transmitting from the Earth, of course, and receiving with the Lovell telescope. We weren't allowed to transmit with the Lovell telescope. I realized the only way I could do it from home was by CW, so I got my CW back to speed, and I was using a rather lovely key called the Swedish key. You can see a picture on the left. I had a 19-element tonner, it's still in my garden, and I actually, because I'm an astronomer, I had it mounted on one of my equatorial mounts, and I'd arranged for it to track the moon across the sky, even though it was daytime and I couldn't see it. So I was actually pointing in the right direction. And at Jodrell Bank, they were able to receive my CW signals, congratulating the telescope on its 50th anniversary. But they obviously wanted some voice, and I was able to arrange some skeds, they're called, with people all over the world, and we got some signals, either voice or CW, from, I think, Scandinavia, from Sweden, from Australia, and from America. That was all rather lovely. Great fun. A good day we had. The telescope surface was really in quite a state by the end of the 1900s. And we were given a grant by the Millennium Commission to take off the surface, clean the backing structure, you can see there, and replace it with galvanized steel plates so they would not rust. There's a work in progress. This was a picture on the 2nd of January, in fact, 1972. You can see that we've actually replaced about a third of it here. They'd actually trial painted this part here, and this was left. Every alternate one had been done. It looks terribly red because the rust was obviously being released as they took these parts off to replace them. But it was in fact just after dawn, and of course the sunlight was very red. Now it has a pristine surface. The paint is one of these two-pot epoxy types, and they now use them on the Forth Bridge, so it shouldn't need repainting, I think, for 10 to 15 years. We used to have to do it about every 5. And that's a picture I took. It's slightly naughty because I took the picture of the moon as well, but they were both taken on different times. A new drive and control system, new drive motors, a sophisticated 10-computer system on the telescope to control those motors to make the telescope track perfectly across the sky. The surface was much more accurate than it had been. I promise you, hand on heart, that telescope is now better than at any time in its history. And in fact, it underwent a third major rebuild just a couple of years ago. The original surface, which was lying beneath the new one, was showing signs of age, really. It might have broken up and perhaps bits would fall down and hurt people in our Discovery Center. So that's been totally replaced too. So it's had 3 major rebuilds in its life. You've all heard of the Lovell telescope. You probably haven't heard of MERLIN, which is an array of telescopes. And if I did one thing of any use at Jodrell Bank, I was a designer and builder of MERLIN, one of 3 of us that did it way back in the late 70s. And also I project managed its upgrade in the 1990s when we added a new telescope, a 32-meter telescope you see up here at Cambridge. So this is an array of telescopes, and we build up our pictures by using something called aperture synthesis. And very briefly, a very crude explanation. If you had a line of telescopes straddling the North Pole and you look down from above, you'd see them rotate round as the Earth rotates. I promise you, if you could combine and collect all the data each of those telescopes collects during that period, only 12 hours actually, you could actually build up an image of the object as if you had a telescope that diameter. Now obviously we're not at the North Pole, and it turns out that we don't make the effect of a circular aperture, we make an elliptical one. We don't really like looking down at the equator, and you wouldn't want to build one of these at the equator. We don't have that many telescopes. It's what's called a sparse array, but you can still actually build up images of the objects you're trying to look at. The first new telescope we built was at Knockin, a little village in Shropshire. I spent a lovely summer down there commissioning it for the first time. It was a very small village. It only had a church, a pub, and a shop. And there was a new owner of the shop more recently, and he called it the Knockin Shop. We used to get our sandwiches there for lunch. So when we use the Lovell telescope in the Merlin array, because it's very big, it doubles the collecting area, it doubles the sensitivity. You all know about the Hubble Space Telescope. It so happens that in the radio, Merlin has exactly the same angular resolution as the Hubble Space Telescope. We can compare our images directly, and we have done a lot of collaborative work with the Hubble Space Telescope. And in particular, this is the Hubble Deep Field. Optical telescopes can't really find out where things are very well. Radio telescopes are much, much better, and we were able to actually locate the positions, not of all of the objects here, but the brightest ones. From then you could actually find out where all of them were, and that's been a very great help in making further observations. Around the turn of the century, we got some money to, in fact, build an extension or an improvement on Merlin called eMerlin. We've got fiber optic links between every telescope in Jodrell Bank. We can carry 30 gigabits of data per second from each telescope. And that means we can have a much broader bandwidth. It gives us greater sensitivity. And also we have very high resolution as well. And that's the sort of image we can make in the radio. And we're now, in fact, using it to observe some of those galaxies in the Hubble Deep Field, to look at the evolution of galaxies in the very early universe. You may remember, some of you possibly, that Betelgeuse underwent a darkening. It dropped in brightness by about 1.5 magnitudes. Christmas not last year, but the year before. And we wondered whether it was about to blow up. Well, it's not going to. It appears it actually ejected a great cloud of dust, which basically trapped some of the light, so it got dimmer. But here is an image made with our eMerlin array, showing it's actually very unstable. It's not now looking like a nice star. It's really quite odd. We do have a role, along with our telescope at Cambridge, and quite often with our Merlin array telescopes, the other telescopes as well, in what we call the European VLBI network. This is the little last example. Here is, in fact, a pair of telescopes not far from the plough. The top one, M82, is called a starburst galaxy. It's undergoing a massive rate of star formation. Very massive stars don't live very long. They become supernovae. And we think there's one new supernova at the heart of this galaxy around every 30 years. You cannot see what's going on because of all the dust. We know it's there. But with Merlin, in fact, we link up with the American array called the VLA, we can actually observe the individual supernova at the heart of that galaxy. And with Merlin, we can actually measure the rate at which these objects are expanding. But we can't see detail. We'd love to see detail. This is a galaxy 12.5 million light years away. By combining our telescopes with telescopes across Europe, although I suspect the one in Crimea isn't being used anymore for obvious reasons, we can actually build an array which is 10 times bigger than the Merlin array, and that means it's got 10 times the resolution. And this is one of the highest resolutions of any instrument of any type in the world. This is the largest telescope in Europe on the right. It's called the 100-meter telescope at Effelsberg in Germany. There's an array of telescopes in Holland. You can see that's equivalent in size roughly to our Lovell telescope. We used to record the data on very large tape decks here, and they were all transported to a place called Dwingelo in Holland, as we'll see. We then moved to hard disk arrays, but now, in fact, much cleaner. It's all done by transferring directly by fiber optic cables. And here at Dwingelo, you can actually see the original tape decks. I can't find a current image, actually, of what goes on inside. They haven't bothered to take one or put it on the web, but that's where the data is collated. And what we can do with that, as you can see, quite a while ago, we actually observed a supernova as it actually expanded over 2 years. So we can make out the structure of objects in a galaxy 12.5 million light years away. That's not bad going, is it? And then, in fact, in 2009, in April, there wasn't a supernova just there. On May the 3rd, there was. And finally, some years ago, I produced this plot showing how the sensitivity of radio telescopes has increased over time. And we'll start off with the original Mark I as 1 in 1957. Now, of course, it's been upgraded quite a bit. It's probably at least 10 times more sensitive now, if not more, as has the Effelsberg telescope in Germany, initially obviously more sensitive than we were, but now also higher still. And then we had the VLA in the USA, and we had MERLIN, which was about the same, actually, a little bit less than that. And then the largest telescope, the Arecibo dish in Puerto Rico, which sadly was destroyed a couple of years ago, a year or so ago, that was in fact the most sensitive. Since then, we've upgraded MERLIN to become eMERLIN, and you can see where that is on the chart. And the Americans have upgraded the VLA to become the eVLA. And together we're very similar in sensitivity, and currently are the world's most sensitive radio telescopes, and we very often work together. We're hoping to do better. But to do better, no one country, I think, could afford what's necessary. So a consortium of about 30 countries has banded together to build up what's going to be called the Square Kilometre Array. It's going to be built in the Northern Cape, the Karoo there, where very few people live, so the radio interference is very, very low, as you can imagine. And this is a sort of an idea, an artist's impression of one of the telescopes. There's quite a few there. You can see there's a lot behind because there's a central core, and that will have several hundred telescopes within it, together making an incredibly sensitive radio telescope. And with outlying telescopes built all across South Africa, we'll have one of the highest resolution instruments in the world, as well as one of the most sensitive. Well, I'm happy to say that work on building the first telescopes of that array started about 3 months ago, so it's on its way. I used to take lots of pictures of the telescopes. They sacked, sadly, or made our photographer redundant, and I was asked to do any photography that had to be done because it's one of my hobbies. And I used to take this picture quite a lot, and I discovered on some plans of a new building, it was called Morison's Gap. Can you see the trees here nicely complement the shape of the telescope? Well, that has gone. In fact, you can see those two trees there, can't you? There and there. This, in fact, is the building, as it was going on, of the headquarters of that Square Kilometre Array, the world headquarters. And that means that the Jodrell Bank site has got a great future. They hope that will be working for 50 years. There's no real reason why our Lovell telescope can't keep working for another 50 years. We look after it very, very well. We do have a discovery centre here, and only last week a big new building, which is about here in the Arboretum, was opened. It's got a planetarium now and a lovely exhibition hall about the story of Jodrell Bank, the early history in particular. And I think, in fact, from now on, it could well be worth visiting. If you're in the northwest of England, on a nice sunny day, it could be a very nice day out. So that's the site as it is now. That building's obviously complete. You shouldn't really thank me for this talk. You should thank Bernard Lovell, sadly died some years ago, but without whose vision, none of this would have been possible. So thank you for listening.
Well, well, Ian, what a wonderful journey. I remember seeing the picture of that as a lad on a stamp, and even on a little stamp, it was
a yellow stamp.
It was, and it was a grand thing to see then, and to see it now and to see the story behind it is incredible. Anyway, for those of you at home been watching this, if you've got a question or you've got a comment or maybe some experience in radio astronomy or something that you'd like to share with everybody and you haven't done it already, please ask it now on either YouTube chat or BATC messaging. And please don't forget to include your first name and your call sign if you have one within every message. So we've got already a couple of questions to start us off.
Right.
The first is from Dino KL0S. Professional optical astronomers have worked more closely with the amateur astronomy community. Any similar collaboration between radio astronomers and their amateur counterparts, do you know?
It's a lot harder, sadly, because to do real radio astronomy, you need to have very, very big radio telescopes, and they're not easy to build. I mean, there are amateur astronomy groups. The British Astronomical Association, the BAA, has got one, and I've actually quite often been to talk to them, and I've talked to groups in Germany as well. In fact, they gave me something quite nice as a result of that, because I was supporting the work. So I have at times, and others have, tried to help amateurs in what they do. It is quite hard to do, and that's why it's not so common as when optical astronomers can work with amateurs. I mean, I have a 12-inch telescope in my back garden, and I can do some quite serious work with that, should I want to do so. I can't claim I do. I like to take lovely pictures of the heavens, or objects within the heavens, but I don't do anything serious, but people do. In fact, amateurs can even observe, and I think on one or two occasions discover exoplanets. It's quite amazing what you can actually do. So sadly, it's not as common, but I think at the very end of this, there's going to be a link to the BAA website where there is a group of radio amateurs. So best of luck with that if any of you want to do so.
Yes, we're actually just going to show that on your screens now. There we are. I won't read it out, but
if you just search for BAA, and you'll find the BAA, British Astronomical Association, you can easily find within there the radio astronomy group.
Yes, thanks for that link, Ian. For those of you watching, if you do miss taking that down, you'll be able to watch this again on YouTube and play it back and jot it down that way. But we'll keep it on the screen just a little bit longer. I'd just like to ask you, I mean, is this a good hobby, do you think? I mean, we're used to in amateur radio, such a diverse hobby. There are so many different modes and different things that we can do. Yes. Is this something that you feel the average amateur can get involved with? Because I had to smile a little bit when you mentioned your small 7-metre dish, because I don't think many of us would consider a 7-metre dish small and something we could put in our garden. So is this something anyway that radio amateurs, do you think, could actively get involved with?
You can do it, but it helps when you have a group, you know, and there's a very good group of radio amateurs, radio astronomers, amateur ones at Cambridge, in fact, and we actually gave them a telescope to use, quite a large one. So it does happen, and the group at the Nottingham Society, they also do some radio observations as well. It's very easy to do observations of the Sun and also Jupiter. And you can also quite easily set up a system to detect meteors. You essentially have a receiver tuned to one of the analog transmitters. I think in Spain they use one particularly. And if you get a meteor traveling across the sky, you get some forward scatter. So you get a ping. So you can actually observe meteors with a relative. That's about the cheapest. That and observing Jupiter, about things that any amateur could do without really any significant cost. But beyond that, it gets a little bit expensive.
And I guess just thinking as well with this, it might be a good way for an amateur radio club to get in contact with a local astronomy club, and maybe there you can combine some of the knowledge and experience and technology and things together.
Yeah, I agree. Absolutely.
That does sound like a good opportunity. Dino's come back, by the way, on a couple of things. He said, by the way, the volume Astronomer by Chance is an interesting autobiography of Lovell. I don't know if you've heard of that.
Yes.
He also says he's in the US as you remember, KL0S.
I thought it must be, yeah.
He's in Virginia, I believe, actually. I made a note earlier. Here in the US, he says the Society of Amateur Radio Astronomers, or SARA, is a similar group. So that's if you're watching this from the States.
Is it West Virginia? Because in West Virginia is the American equivalent of Jodrell Bank called Green Bank, which is a wonderful telescope, 105-meter telescope, and I've been there. And in fact, I gave some talks about radio astronomy when I went to a conference there many years ago now, actually. Anyway, yes, carry on.
No, that's all right. Well, thank you for that background. On that, I mean, you said that you recently upgraded your control systems and the dish surface itself relatively recently. You've done those with galvanized sheets and things. Has there, because a lot of us watching this are interested in the electronics and the technology side, and we've seen lots of advances in our own ham radios, have you made upgrades as well to the electronics to increase the sensitivity, maybe?
The only thing that affects the sensitivity are the receivers, and they're now as good as you can possibly make, as I intimated earlier. The fact that the surface is much smoother means that the efficiency of the antenna is higher, so that helps a little bit, but not an awful lot, to be honest. It depends on what wavelength we're using. When we use long wavelengths, 408 megahertz is about the lowest frequency we use, not far from 432. And I should perhaps have said that when we did that moon bounce, we actually adjusted one of our receivers from 408 to 432, so we could use it for doing EME. That was great fun. Anyway, that's all helped a bit, but the main thing is that now the computer systems we have to analyze the data are getting incredibly powerful. To combine all the data from our MERLIN telescopes, we built a special purpose device. It's actually housed in a Faraday cage to stop the interference getting out. But in fact, that's now being replaced, and the equipment's just arrived at Jodrell Bank about 3 days ago. Basically, by that was a correlator, it's called. It's now a software correlator. And these use lots of GPUs. You might have heard of those. Mm-hmm. They're very often used for computing, not just for doing graphics. So things are changing quite rapidly. And of course, with fiber optics, we can now link our telescopes up and send data across the world, not instantaneously, but very quickly. And that allows the telescopes across Europe, in what we call the EVN, European VLBI network, to basically act in real time. All the telescopes are sent to Groningen and combined together, so we can tell, which is great, everything's working instantaneously. Because in the past, we have about polarization. Well, we have to set up our antennas on our telescopes to give us a particular polarization, left circular or right circular. On one occasion, half the telescopes in the European network were on right and half were on left, and no one found out until about 4 months later when all the data was combined. So now it makes life much easier.
I'm sure. Ian, can I ask, you said this, and I believe in your synopsis, you said that this is your 57th year involved with Jodrell Bank.
Yes.
So can I ask what you do there now?
Not an awful lot, particularly since COVID happened. We've been having our meetings in Zoom, in fact, on Wednesday mornings, and sometimes as well as that. I have been building some receivers. In fact, some of you I know you all know about the Raspberry Pi, but there's a thing called the Arduino. Have you ever heard of that?
I think many of our viewers will have done, yes.
Yeah, well, that's the Italian sort of version. And I was able to build a pulsar receiver using an Arduino to observe pulsars with one of our telescopes. And that actually is something that, in principle, amateurs could do. And my paper about that was sent across to a group in America who might be trying to have a go. So, that's one recent thing. I'm a bit of the historian for Jodrell, and I wrote a year ago an article for Nature about the history of Jodrell Bank, which is quite nice. I do produce a website every month about what you can see in the sky. That's on our observatory website. But I haven't done anything particularly technical, I think, for the last 2 years, because really we haven't been able to go to Jodrell Bank.
No, of course. I suppose, though, that's where some of the communications and I presume a lot of this you can look at remotely now with the technologies available.
Most of the work I can do on my computers at home. So that's a great help.
You mentioned about it's a good thing to go and see. In fact, one of our viewers said that he actually goes Combat Wombat 71. I don't know your call sign. I'm sorry, that's your name though on YouTube. He says I always try and catch a glimpse of it from one particular spot when I'm driving north up the M6.
Yes, so you can do.
And you said this is a wonderful site to come and see. If you go there, is there a visitor centre or anything, or is that closed as well at the moment?
That's what I was trying to say.
That's closed.
It's now called, it was a discovery centre, but it's now called something a bit more than that. We've been gradually building it up over the last 14 years, I think. But we were able to get a £20 million grant to build what they call the Discovery Dome, I think, which in fact is the same size and diameter as the Lovell telescope. It's a grass-domed building. Inside we've now got a very nice brand new planetarium, which can also show IMAX films beautifully, and a wonderful display of the early history of Jodrell Bank, along with all the other displays that we had before, and the lecture theatres and the like. So now, on a reasonably summer day, so you can walk around, because there's quite a lot of walking to do around the site. You can walk right round the Lovell telescope, the base of it, and get very, very close to it indeed, and see the other parts as well. You can't go into the observatory itself, I'm afraid, but you get very close to it and can look into it. And I would say that's now worthwhile visiting.
And do you, if you do know this, and I'm sorry, this is an unfair question, maybe without notice, but do you have to get tickets or anything to do that, or can you just walk around, arrive, and
no? Well, you have to arrive. Slightly annoyed. Apparently, it's got a lovely new car park, and to pay for that, you actually have to pay for parking.
Right.
And then I think you obviously just pay to go in. There's big new pay booths, a bit like you see at the front of some of the theme parks, which I saw. I went there to visit. We had a lovely evening, with cocktails and things like that, just about a week and a half ago, just to show us what the new building was like. So now I think it's worthwhile visiting. I really do. Well, so just turn up.
With the summer now with us, I'm sure that it's something that a lot of people will consider doing. Ian, thank you. I think we've exhausted all the questions so far on this. Lots to think about, and lots of good comments. You won't surprise you. For example, Graham G0DMU says he seems to recall a project called Jove from NASA for some research, and also one called Radio Skypipe, and he's found the details of that on the web. Retro Jimmy says, such an interesting presentation. Thank you. Amazing range of applications throughout the telescope's history. And I think I'll leave the last word with Simon M0JQM, who says, thank you so much for this presentation. It's been a real eye-opener and an inspiration for further study. I love the avenues that amateur radio opens up to us. So I think that's a lovely way.
Thank you very much for those.
Also must mention Jeff ON8NT as well from Belgium, but lots of others as well watching. Ian, thank you very much. It's been absolutely fascinating, and I'm sure that next time I'm off up that sort of direction, I'm going to not only look for it, but I'm going to go and have a look around it as well. Thank you.
Very good. I hope you enjoy it. It's been very nice to be with you. All the best to everybody.
Thank you very much. Thank you. And that concludes this webinar, and thanks once again to our guest, Professor Ian Morison, G0DMU. Thanks also to Studio Director Tammy Palmer, M0TC, and the RSGB team who helped put this series together behind the scenes. We hope you've enjoyed this Tonight at 8 and that you'll be able to join us next time when Peter Duffett-Smith, G3XJE, will discuss all things aerials, from the basic radio wave to antenna resonance and matching and so on. And if you'd like to see details of this and other future webinars or recordings of past editions, please visit rsgb.org/webinars, where you can also send us comments and feedback. And a reminder that if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. But until next time, this is David G7URP signing off and clear. Bye-bye.